We saw last time that a regular Markov chain converges to a stationary distribution in long run. This we proved formally, and if that didn't convince you, the beautiful demonstration in the last class should have convinced you that if you run a regular Markov chain, in a long run, it goes to a stationary distribution, where the stationary distribution was defined as a probability vector W such that this happens, which amounts to saying that it's a eigenvalue 1 eigenvector for M transpose, where M is my transition matrix. Important thing to note here that stationary distribution is only a property of M. It does not depend on the initial state. Now, today we will see an application of this in page rank algorithm. This is a pretty practical problem which I'm sure all of you have worried about, which is basically how Google works. You give a query to Google and then it ranks the pages. There are multiple parts of this. Two important parts are rank pages according to their importance, and the other important part is the similarity with the query you have given. In general, these are the two important parts. There are more parts in there, and all of this constitute Google's algorithm to rank pages. I'm not going to tell you about them because obviously it's a secret. What we are going to do today is concern ourselves with the first, how to rank pages according to their importance. This is the question we are going to deal with today. This is one of the very important parts in Google's algorithm, and we will see an application of Markov chain. This important thing, this again does not depend on the query. So we will ignore the question of how to find similarity with the query. We are only going to deal with the first part. You are given internet, a lot of connections between web pages, and we want to rank pages according to their importance. Many questions, how do we find importance, how do we rate them? So let's see what is the input first. The input is basically the World Wide Web. We can model it as a directed graph which captures the connections. How does it do it? The graph has set of vertices, which is the set of web pages. For edges, I comma j is an edge if web page I links to web page j. Makes sense? Let's say this is Google, this is Microsoft, and you can ask Apple and so on. So all these are web pages. Let's say my home page, since it's very important, everyone links to it or something. But this is the picture. This directed graph is given to us. Question we are asking is to rank these pages according to their importance. Here, the importance is not defined. That's something which we have to figure out. Let's take the first idea. If page is linked to many other pages, that means many other pages take you to the page, let's say I, then I seems to be important. One of the simple measure of this could be that we say that the importance of the page is the number of edges coming to it, in such sense in degree of the edge. I am just summing up over all the web pages which are coming to I. So this is the in degree of I. Remember, it's a directed graph. If many pages link to the some page, then clearly it is very, very important. This is a nice attempt. There are few problems with it. Particular two problems we'll talk about. There might be pages which have lot of connections going out. So in some sense, their weightage should be less. So if we have a page from which we have 10,000 connections, then its weight in this equation should be lesser than if, let's say, there is just one or two connections from a web page or something. So pages with more connections, more out degree should have less. Another thing, intuitively it seems that important pages should be given more weight. If my page connects to yours, that should be less important as compared to if say Apple's page connects to your page. And you immediately realize that this is kind of a recursive problem. Seems hard. Let's see. Is there an easy way to take care of it? For the first sense, we see that it's very easy to worry about the out degree. We say that pi j such that ji element of E 1 by dj is the out degree of J. Now I'm weighing according to how many edges are going out. So if I have a connection from J, but there are a lot of connections going out from J, then the contribution is small. If if the web page I has a connection from J and J has very few edges, then the contribution is more. So first thing is taken care of. But how about importance? How should we, so we want to find importance, but we want to take care of importance. How should we do it? Let's take a completely different viewpoint of the problem and see how Markov chains will help us. We are going to model a person suffering web. Okay, I shouldn't say suffering, I should say surfing web, but we also know that a lot of people suffer from web also. But let's talk about surfing here, right? So a person surfing web, we want to model it. What happens? The person starts at some random page. There are some connections going out at some time step. He moves to the one of the pages which are neighboring to it, whichever ones are connected. From there, after a time step, he would move to one of the pages. So this is one, then let's say he moves to two, then he has two options, he moves to three, and so on. And this keeps happening. What does this remind you? It reminds you of a Markov chain. This is a Markov chain with nji being equal to 1 by dj. Again, this is the out degree. Right? So we are in some state, and with probability, if we are in state j, with probability 1 over dj, we move to another state. So if we model a person surfing web as a Markov chain, what should happen? You remember that a Markov chain converges to a stationary distribution. So that means even this Markov chain will lead us to a stationary distribution. But how should it give us rank? Now it should be intuitive to you that W is a probability vector over all the web pages. In that sense, the weight of a vector in W should be proportional to its importance. This gives us a method. Using M, we should find its stationary distribution W, and once we have W, we rank according to the entries of W. Remember, one entry of W represents one web page. So we just sort them out, and that would give us the ranking. Sort W, and that should give you the ranking. But we forgot a small detail. What if M is not regular? It was not given to us. If M is not regular, then it might not have a stationary distribution. What should we do? First exercise you should do is create a Markov chain of this person surfing the web, which is not regular. So just by our description of a person surfing the web, the Markov chain is not going to be regular. We will change our model slightly. What is the change? We will assume that at every step with probability P, we can just go to some arbitrary page. You could say that the person starts afresh. The person gets bored of the page he or she is looking at and says, okay, I'm just going to go to an arbitrary page. And this happens with probability P. With probability 1 minus P, you can just go to the link like before. So this you will do with probability 1 by Tj. Seems like a very natural model. This is probably how many of us surf. And here, P is a parameter which can be changed to make it more accurate. So what we have done is defined another Markov chain, which is this entries. So this happens if J is linked to I, and if J is not linked to I, then you have just this P by N term. J is not connected to I. This is the new Markov chain. Easily, it can also be thought of as a combined matrix, where J is the all ones matrix. Great. So now we have a new Markov chain, and you can easily prove that this is regular, and hence will have a stationary distribution. So our entries could be ranked according to this stationary distribution. P can be figured out by experience and things like that from the previous data or something. This is one way. There is another way to do the same thing. That means we will again model slightly differently, and we will see that we will end up with a regular Markov chain. This will once again give the ranking. So remember, we changed the model, we changed M prime, we said that a person can randomly go to some other link. Let's take a different model, but before that, I have to introduce you to something called an ergodic Markov chain. Again, it depends on the transition matrix, and this says that a chain is ergodic if for all ij there exists an n such that this is greater than 0. It looks very much like regular Markov chain, so let me just write the definition. Sorry, I should say there exists. So you notice that the order of quantifiers are different in these two. As an exercise, you can show that a regular Markov chain implies it is ergodic, but this need not be true. Again, you can come up with a counter example. So it's easier to find ergodic Markov chains rather than regular Markov chains. Ergodic Markov chain in our case of surfing the web amounts to saying that we have a connected graph. And that's not much of an assumption, right? If the graph is not connected, you solve the problem on the disconnected components. And then they are independent of each other. There is no way to rank between them. So that is one way. And now, but we also don't know whether an ergodic Markov chain converges. So what we are going to show is a generic method to convert an ergodic Markov chain to a regular Markov chain. If this is M, then M prime is defined as half I plus half I. In terms of surfing the web, this is again very intuitive. What are we doing? We are saying that at every time step with probability half, we move to a link. And with another probability half, we stay at the same page. And you can kind of see that this half is arbitrary. You can choose some other probability also. And still, this quantity, this Markov chain will become regular. I leave it as an exercise for you to show that M prime is regular. If you can't do it, then it is actually shown in the notes. So you try it yourself. If you can't, then you can see the solution in the notes. So what we have seen is that we can model our problem so that we get a regular Markov chain. Our algorithm is find W, the stationary distribution of the Markov chain, and then sort the entries of W. And this will give us a ranking. Now, some of you might ask, how do you do this? And this is a very, very interesting computational question. In general, for a small enough matrix, finding a one eigenvalue eigenvector is not a difficult task. It's basically solving a bunch of linear equations. But in the case of surfing the web, these linear equations are going to be huge. The number of linear equations are very big. But if you note, most of these are very, very sparse linear equations. That means the connections from a web page are like of the order of 10 to at max 100, 200 or something. On the other hand, if you look at the number of nodes in the graph, that would be of the order of billions. So this is a system which is very, very sparse. That means most of the entries are zero. It's a big, big question in computer science, how to solve sparse linear equations. This is a big open question. Not an open question, I would say, but a question where people keep making progress. And very, very practically important, for the reason being this page rank algorithm. This will end our introduction to Markov chain. We have only one lecture remaining. We'll talk about another new topic which we call probabilistic.